Meet the man who taught the world how to see. Long before the Renaissance, Abu Ali al-Hasan ibn al-Haytham was revolutionizing our understanding of the physical world. Born in Basra during the golden age of Islam, he wasn't just a scholar. He was the architect of modern light. By bridging abstract mathematics with rigorous physical experimentation, he proved that light enters the eye rather than leaving it. This fundamental shift laid the groundwork for optics, astronomy, and the very scientific method we use today. He truly changed how humanity perceives the universe. To understand the Islamic Golden Age, we must see nature as a form of worship. Historically, the Greek tradition kept physics and mathematics in separate worlds, one dealing with tangible, dynamic flux, the other with abstract, unchanging truths. But a new paradigm emerged with Ibn al-Haytham. He dared to merge these two disciplines into a single science. By demanding both empirical observation and mathematical proof, he essentially wrote the first draft of the scientific method, proving that the universe is governed by logic we can measure. Ibn al-Haytham's greatest breakthrough was born from a death-defying gamble. Appointed by the impulsive Caliph al-Hakim to dam the Nile at Aswan, he soon realized the project was impossible with 11th century technology. To escape the Caliph's certain wrath, he famously feigned madness. This led to years of house arrest near the Azhar Mosque. Yet in this forced isolation, his mind remained free. He spent his survival years studying the works of Ptolemy and Euclid, ultimately incubating his masterpiece, Kitab al-Manazir, or the Book of Optics. Truth is not found in blind inheritance, but through relentless skepticism. Ibn al-Haytham believed that a true investigator of science must make himself an, quote, enemy of all that he reads. By this he meant we must challenge every existing theory and, perhaps most importantly, suspect ourselves during every critical examination. He warned us against the arrogance of certainty, arguing that truth must be sought purely for its own sake. It is this unwavering commitment to doubt that lights the candle of discovery. Ibn al-Haytham transformed science from speculative philosophy into a rigorous cycle of reproducibility. This process, known as al-i'tibar, begins with observation of natural phenomena. Scientists then hypothesize a geometric and physical explanation before moving to controlled experimentation, such as isolating light sources. Finally, results are recorded and evaluated systematically so others can replicate the findings. This radical departure from ancient traditions shifted the focus from why things happen to how they can be proven through evidence. Before Ibn al-Haytham, the world was divided on a simple question: how do we see? On one side, the emission theory of Euclid and Ptolemy suggested our eyes shoot out beams of light to touch objects. On the other, Aristotelian intromission theory argued that an object's form is physically introduced into the eye. The problem was a massive disconnect. Mathematicians had the geometry right but the physics wrong, while philosophers had the physics right but lacked the math. The stage was set for a genius to finally unite them. How do you prove the invisible? Ibn al-Haytham used a simple dark room and a few candles. By placing candles outside a small aperture, he observed that shielding one flame only extinguished its specific light spot on the opposite wall. This was the aha moment for optics. It provided physical proof that light travels in straight lines from a source, through a point, and into a recess. He had effectively created the camera obscura, proving once and for all that light travels into the eye, not out of it. Having proven that light enters the eye, Ibn al-Haytham turned his focus inward to decode the anatomy of sight. He identified the cornea as our clear outer shield and the uvea as a dark tunic providing essential shading. But his most brilliant insight was the orthogonal rule. To prevent a chaotic blur, he theorized that the glacialis, or lens, primarily accepts light rays reaching it perpendicularly. By refracting and weakening oblique rays, the eye filters the world into a coherent, point-by-point image. Sight begins in the eye, but vision is completed in the mind. While the eye acts as a photoreceptor to receive light, the process of seeing is far more complex. Ibn al-Haytham identified the optic chiasma as the crossroads, where binocular images unify into a single sensation. He argued that true cognitive perception occurs in the brain's anterior. Ultimately, we do not truly see through light alone. It requires psychological layers, our memory, imagination, and discernment to transform raw data into the world we recognize. How do we know how far away an object truly is? Ibn al-Haytham's ground theory explains that distance perception isn't magic, it's a calculation. He argued that for us to judge distance accurately, the object must lie along a continuous visible surface like the ground. We then use bodily calibration, scaling what we see based on a lifetime of walking and reaching. However, this certainty has limits. If an object is at an immoderate distance, our spatial logic fails, and clear perception degrades into mere conjecture. Ibn al-Haytham's genius wasn't limited to physics. He tackled mathematical puzzles that would stump scholars for centuries. One such challenge was finding the exact reflection point on a spherical mirror between a light source and an observer. Known as al-Haytham's problem, it is the geometric equivalent of a billiard ball's path on a circular table. Using intersecting conic sections, he provided a geometric solution so complex that an algebraic proof via a quartic equation wasn't achieved until 1965, nearly a millennium later. Long before the modern era, Ibn al-Haytham challenged the very definition of place. While Aristotle viewed space merely as a two-dimensional boundary containing an object, Ibn al-Haytham used geometric proofs to expose this as a mathematical absurdity. He disrupted the ancient view by redefining space, or al-makan, as an imagined three-dimensional metric void. By proving that space exists independently of the bodies within it, he set the stage for Descartes' extensio and Newton's absolute space, fundamentally changing how we map the physical universe. The impact of Ibn al-Haytham's genius was not confined to the East. By the 1200s, his masterwork, Kitab al-Manazir, had reached Europe as De Spectibus. His theories found powerful champions, such as the English empiricist Roger Bacon, whose work pushed the established timeline of the experimental method back by 2 centuries. Most practically, his complex mathematical formulas for refraction crossed into Italy, providing the scientific foundation for the development of the world's first eyeglasses. His legacy is quite literally how many of us see today. Ibn al-Haytham's influence even reached the canvases of the great Renaissance masters. While he provided the perspectiva naturalis, the mathematical mapping of how we naturally see, later architects like Alberti and Ghiberti took his rules further. By applying his translated principles of light and distance, they developed perspectiva artificialis, or projective perspective. This breakthrough gave artists the power to construct realistic, three-dimensional depth on entirely flat surfaces. The realism we admire in Renaissance art is, in many ways, a direct result of medieval Islamic geometry. Ibn al-Haytham's legacy bridges the gap between ancient reason and modern discovery. In 1647, astronomer Johannes Hevelius honored him alongside Galileo, placing him on the pedestal of reason in his lunar mapping book. Today, that same spirit lives on as we gaze through the 3.2 gigapixel camera of the Vera C. Rubin Observatory, the ultimate modern pinhole. Ultimately, his greatest gift was not just the science of optics, but the courage to doubt, test, and seek truth purely for its own sake. The journey of light that began in a dark room in Basra reaches across a millennium to the very edge of our universe. Ibn al-Haytham's influence was so profound that by 1647, the astronomer Johannes Hevelius placed him on a pedestal of reason alongside Galileo in his famous lunar mapping book. Today, we continue his work using the Vera C. Rubin Observatory. Its 3.2 gigapixel camera serves as our generation's ultimate pinhole, capturing the cosmos with a precision he could only have imagined. Ultimately, Ibn al-Haytham's greatest gift to humanity was not a single discovery, but a mindset. He gave us the courage to doubt established wisdom, the discipline to test every hypothesis, and the relentless drive to seek truth purely for its own sake. From the flicker of an ancient candle to the digital skies of today, his legacy is the light of the scientific method,